So it consists of nodes and edges connecting the nodes. In addition, the vertices of the graph, the nodes will be decorated by integers. So there will be a1, 2, a3, a4, and so on. AI.
But the horse is nicer.
Well, I think what's illustrating is that we can choose lots of different graphs. So the input data in the stock will be your choice. So you can make another version, probably much better than mine, of a graph. We can take thinking diagram, whatever we want. And it's a decorated graph. So again, vertices are decorated with integers. On the other side, it will be a slightly different structure. So I'm going to migrate here. That's the other picture from the slide. It will be a picture of a quiver. So what quiver is somewhat similar to combinatorics, where there are vertices connected by, instead of edges, rather arrows. And there are different versions of quivers. So I'll use the one in which for every arrow going from one node to another, there will be a return, and there will be equal number of those. So for instance, this could be a reasonable combination, something like this.
But not self-arrows, arrows from one to another.
And I will allow self-arrows. So for example, let's keep this clean, or maybe we'll put one self-arrow going like this, no self-arrows here, and maybe two self-arrows. Well, let's do three. Okay.
But they don't need a partner.
Yeah, for self-arrows, you don't need a partner because they're already going from same node to the same. So at a very basic level, what I'll present is connection between these two structures. That structure will be more relevant for topology, as we'll see. This structure is very common in representation theory, curve counting, and many other concepts. So there is geometry associated to such. This is called quiver, called quiver variety. That would be the geometric concept. Now, in both of these pictures, there is a matrix associated to it. So going back to this side, here, the natural matrix that I can associate to this picture is the following. I'll call this matrix Q, and it's going to be of the size as many vertices we have in a quiver. And each time we see an edge between vertices I and j, let's go, we'll put one here in position ij. So QQij will be equal to 1 if I and j represent an edge in this graph. And for simplicity, let's assume that it's more like on the slide rather than here, so it doesn't have loops. That will be easier. We'll put AI in a diagonal position. If I is equal to j, then this first rule cannot be applied, but instead we'll just use more natural one. That's why we had integers. And we'll say that it's 0 otherwise. So that's the natural quadratic form or symmetric matrix associated to this data. On the other side, there is also a natural quadratic form or matrix that we can associate to this figure. I'm going to call it C. And it will be also of the size as many vertices we have. So here it will be, in this example, 3 by 3. And what we'll do on a diagonal, we'll put number of self-arrows. So if this is vertex number 1, 2, and 3, for example, on a diagonal, we'll put 1, 3, and 0. Then for each pair of vertices, I and j, which are connected by an arrow, we'll put a corresponding off-diagonal value to be representing that number of arrows going in. So for example, between 1 and 2 and 1 and 3, we have only 1 going in each direction. So it will be 1, 1, 1, 1 here. And here we have twice as many, so we'll put 2s here. So that will be same kind of connectivity metrics in the context of this quiver on the quiver side. So the biggest mistake one can make during this talk is to confuse these two matrices. They're both symmetric. They both represent some connectivity structure, but they will play completely different role. And they're not the same. So one is called Q, the other is called C. One is on actual blackboard, the other is on a whiteboard. So there is no way they can be the same.
So the symmetry is like a condition on this.
Yes, yeah. So let's assume that they're, I mean, the arrows go back and forth, so it's completely symmetric. So the punchline that I'm trying to tell here in the beginning of this talk is that we'll start with the data here, and we'll call this sort of data y, for example. That's the basically the graph with all this data. And then from here, we'll go to the right. So I'll go this way, and we'll continue. And associated to picture on the left will be some kind of Q-series. In fact, a collection of such. So we'll have basically some numbers and I due to the I plus some delta. So this will be some Q expansion, all determined by information on the left-hand side. And our goal in this talk will be to ask what kind of Q function is it? So that's my main question. That's what I'm going to discuss. Starting from that side, we'll migrate here and ask what can we say about it? It turns out that it will be a function of a very specific type, and that this Quivers structure will encode the answer to this question. A priori, it could be anything. I mean, it could have coefficients which are growing very fast or very slow. Anything could happen. But it will be of a very specific type where all the key data will be completely encoded in terms of this metric C and the corresponding quiver. So that's why I'm putting it on the board. So namely, it will be a multisum. So it will be sum over integers. Let's call them, for example, di, greater or equal than 0. And they can be many of those. And then we'll write a simple, each term in the sum will be a simple ratio of q to the half d dot c dot d, basically a quadratic form associated with this symmetric matrix, plus possibly something linear, which will be much less important. For example, if you want to estimate the growth and so on, the quadratic term will be much more important. And denominator will be completely universal. It won't even depend on choice of C. It will simply be a product over these i's of Kuperheimer symbol with coefficient di. So that's the punchline. That's the summary. So there will be, in the end, some equivalences on both sides, and they'll have a meaning. They'll be completely different. And again, matrices Q and C are completely different. But in principle, this is huge class of problems because obviously there are many graphs here that we can choose, and this course is just one representation of it. Obviously, there are as many as stars in the sky or fish in the sea. And likewise, there are lots of Quivers you can pick, and there is some kind of connection.
Oh, is it definition of left-hand side, or is it left-hand side somehow defined independent? That's identity.
The left-hand side will be defined using that picture.
It's not
So I'll give
yet.
a definition in a moment. And then the answer to my question, what kind of, so a priori from that definition too, it won't be clear what kind of function of Q it is. Is it, I don't know, for example, eta function or some modular form? Or is it just 0 for all the choices? So that we don't know. But this will be the answer. So I'm giving away punchline. So movies usually don't do this. But if you can basically skip the rest of the talk because this is basically going to be the answer. My job, in fact, in the remaining 50 minutes is to explain why this answer is interesting and deep and so on. But I want to emphasize with this introduction that it's a very combinatorial problem. It's a very, I mean, it has combinatorial flavor because objects, despite the depth, are pretty simple, encoded in this kind of stuff. Good so far?
Is typically Q much larger than C?
Huh?
Is typically Q much larger than C?
Q is typically much larger than C, that's true. And I don't know why that is. In some sense, the reason to present you this as a duality, and I'm sure these two blackboards, is to illustrate that there is something interesting going on, and finding better dictionaries between two sides is something that would be open problem.
Yeah, but say this here, the left-hand side has a number of bits of information. It remembers Q up to a point, or it remembers Q, I don't know.
It remembers Q up to, there will be, like I say, some equivalences, maybe the better way to that shows up.
It kind of remembers Q.
It kind of remembers Q, and most importantly, it's a very good question. It remembers most essential information about Q. So what that means, I don't know precisely, but again, everything.
Some spectral information on the graph or something.
Oh, that's an even higher level version of this question. That I don't know. That I can't demonstrate later. But it's a good. I mean, what you're thinking of is exactly the right question for where I'm going to leave the subject and hand it to you guys in the okay, so then so what I'm going to do next is we'll forget about this side for a moment. I'll start here. I'll give you a definition of how to associate this Q-series, and then we'll start inching toward this Quiver, this presentation. So I'm going to erase this and
but naively, just very naively, is a little bit of a compression of information formula, because this matrix is much smaller.
Like I said, I don't actually know to what extent. Let's see. I'm trying to navigate the slides.
You have to click the mouse on this.
Yeah, I'll click the mouse.
Oh, okay.
Yeah,
Sorry.
that's okay. There you go. Now you should be able
Does it
to.
work? Yeah, so slides here basically say everything I said before. So this is the definition of Q and C that we already discussed. The connection will go through some Q series, which will have this form. And right now, I'll go to the definition of this Q series that we have. So we'll start with the data like here or on the left-hand side. And we'll define, so that's the definition. We'll define a Q series. I'll call it Z hat, which is labeled by choice of graph over there. And it will be a function of Q, and it will also depend on additional labels B that you can ignore for simplicity. And it will be defined as a multiple integral. In fact, contour integral, where the integration will be over variables associated to vertices of the graph. So here in this part, I will run over a set of vertices. And for each one, we'll have one-dimensional complex integral to do. So we integrate over dxi over 2 pi I xi. And we'll integrate over unit circle. So first thing I have to tell you about this integral, what is the domain of integration? We're going to integrate some function which will be holomorphic in this axis or meromorphic, and we'll integrate over one unit circle for each of the variables. So integrand, likewise, will be the product over vertices, and it will have the form xi minus 1 over xi to the power 2 minus the degree of the vertex I. Degree is the valency, so it's number of edges that come to it. For example, this one will have degree 3, this will have degree 1, and so on. In fact, this product or this component of the integrand you already saw in the previous talk. So at least it showed up. And then we'll multiply this expression by a theta function. So remember, I told you in the beginning that we had both crucial information associated to both sides of this correspondence, the quadratic form. So once we have quadratic form, it's a crime not to write a theta function based on this quadratic form. So that's what we're going to do. It will be a function of all of these variables xi. It will depend on q, and it will be quadratic form, capital Q defining the theta function. That's where this pesky little labels B will show up. This will be characteristics of the theta function. So if Q is unimodular, there will be no B at all to worry about. So that's the definition. Okay.
Are you going to tell us more about the theta function, or?
Yeah, so it is what you think it is. It's absolutely, so actually here on the slide I walk through this definition. You can give it more kind of local piece by piece, like Lego decomposition. You could say that for integrand, to each vertex you associate this, to each edge you associate this, and that's what I just wrote. So this is principal value or graph inversion of the principal value integral, like that kind of stuff. And since you asked me about theta function, that's the function. Again, there is nothing surprising. It's basically a function which is summation of a lattice. Size of the lattice is determined by number of vertices. For example, for this 4C, the number of vertices will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 10, 11, 12. So there will be 12-dimensional sum to do, so it's huge. But it is what we think it is, namely Q is raised to the quadratic power of the summation variables and X's are raised to the linear powers. That's the normal definition. And Joseph is probably noticing a factor of 2, which has to do with spin structures.
So
Am I right?
You don't have it there.
Here I sweep it under the rug for simplicity, but it is, of course, there. So I try to sweep anything unimportant to me, and again, experts may spot me doing that. One of them is in the audience. I should say that some of these questions, like what kind of functions they are, how they behave, is based on what we're exploring with Ludmila and Joseph, and that's why we have really high-level experts in it. But anyway, coming back to the definition, that's basically the starting point. So that's the mathematical. So, any questions so far?
So what field theory motivates the introduction of this integral? What's going on? It is a partition function, I assume.
It is a partition function. Yes, that's right. You're absolutely correct. It's easier for me to answer it in terms of a numerative problem. So as a partition function, it's counting something. That's why I wrote here coefficients for ni, suggesting they are integers. So I will come back to this in a second. I can attempt to give a better answer to this question maybe in the end, but I wasn't prepared for that. Okay, so we have a definition. So next goal or next step is to explore what it is. And one simple theorem. So that would be theorem 1. And by the way, I'm going to assume that you already see it here, that Q is negative definite. So here for this, and in fact for the statement of this theorem, this will be crucial. So if Q is negative definite, with this assumption, this object that we just defined, which depends on Y, depends on Q, and there is this label B, I'm not sure if I'll be carrying this all the time, is convergent in the unit disk. Okay? That's not a very sophisticated theorem. You can just do it by ratio tests or I mean, it's behaving really well. So any simple way of attacking it will get the result. Second theorem, which is something I already announced before, is that for any choice of this input data, it has integer coefficients. In other words, this object as a function of Q belongs to Z of Q, where I should probably also multiply by this. There could be overall offset of offsetting factor, but otherwise it has integer powers and integer coefficients. And like I said, that's kind of important because where it came from has to do with counting things. Associated, again, to the graph that was the input data for the whole problem to start with. So next statement should have, so this at least a little bit tells us what kind of object it is as a function of Q. but it also depends, more importantly, on the choice of the graph. So next question is, how much does it depend on the choice of graph? For example, if it's 0 for all choices of y, then yes, both conditions are satisfied, but it's not terribly interesting object, right? So we should try to see what it is. And so for this, I prepared a little illustration. So let me try to. Oops. So how do I exit the? Oh, okay. Here we go. Yeah. So let's do a Mathematica demonstration. So this is a simple Mathematica code which implements the definition I just gave you, and I'll be happy to share it. And in fact, I think I already shared it on the website, so you can download it and play with it. So what it does, it's basically taking input information of the graph y on the left-hand side of our discussion. So you can literally here, and I'll do it for you in a second, input all the data, namely all the coefficients, vertices, connect them, and then draw a horsey or linking diagram of your favorite group. And then it basically computes this kind of Q-series. So here, I just ran it a minute ago to make sure it works. And I think it does. So for this graph, so let's do it again, just so you see it. I evaluate it, and I scroll down to the bottom where it's computing the integral. By the way, I'm not going to digress on this too much, but I should say that even though I gave the definition as a multiple integral, we can do it by residues, and it quickly boils down to very simple combinatorics, which doesn't involve integrations. So it's again very, very simple, and that's what the code is doing. It's not really computing any integrals. It's basically assembling the remnant of the residues into the final expression. Anyway, and for this particular graph, which was the original input data, we see what it is. It's some expression. It exactly has the form that claimed in the theorem too, namely up to overall fractional power of q. It's a series with integer powers into the group.
So how surprising is that it comes out with integer coefficients from the residues? I mean,
it's not terribly surprising. Like I say, these theorems will be going in slightly increasing degree of complexity. So this one is really easy. This one is a good exercise for a graduate student. This one is also good, but they're getting harder. So this is not too hard. In fact, I probably presented it in a more mysterious way than it really is. I mean, looking a little bit under the hood immediately makes it clear that it's a fairly simple object. It's basically convolution of theta function with some rational function. That's all that was.
Typically plus minus 1, or?
No. In fact, I should have said, and that is going to be important for me in the talk, that here, what this code computes and the way I define it on the board is a definition where I actually remove 1 over Beheimer q infinity from the denominator. And for me, it will be important to include it back. So if I do even with this, multiply namely this answer by this function, it will quickly mess up coefficients. So they will become not just plus minus 1. So I want to. So like I said, I stripped off some of the elements, and this is, since this does not depend on the choice of graph, I thought, oh, I should remove it as well to save space, but that's actually probably was a bad idea. But yeah, that's another good observation, that sometimes there is some regularity here, and yeah, that's what I should explore. Good news is that it's not 0, so at least that's good news to me. So next question is, does it really depend on initial choice of this graph y that we introduced as an input? So let's mess up this computation a little bit. So I'll go back to the computer. And what I'll do is, let's see, I'll add another vertex here. So I'll say that 4 is now going to be connected to a 5. So there'll be 5 vertex graphs. So I'll change it. And I'll change some of these integers as well. So I'll mess it up a little bit. We'll ask Mathematica to forget everything that happened before and do this evaluation again from the start. And by the way, before we do that, let's just save the previous answer so that we can have it at our fingertips if we need it. So yeah, let's do this calculation again and see what comes out. Yeah, so for some reason it's now.
But this computer is for small presentations.
Well, actually, I think it's an issue with Mathematica because I have the same on my laptop, so it doesn't do very much. For some reason, running second time something is taking more time. Let's see, I hope it doesn't take forever, so I don't know. Yeah, this is obviously a little longer than expected. Oh, here it is. It's one of these things where, you have to try to roll the mouse, or even though it shouldn't make a difference, but somehow magically it does. So anyway, first let's go back to the graph. So see, it changed the shape. It was much simpler before. Now it has different numbers attached to vertices, different structure. This computes eigenvalue, so we can double check it's still negative definite. So that was one of the tacit assumptions that we briefly mentioned. And more importantly here, what happens is that this line here is the answer saved from the previous calculation. So this line here is the result of computing it right now with the new edges, vertices, and so on. And as you can see, it actually didn't change. So what this tells us is that whatever this machine does, it associates collection of Q-series not to each individual graph, but rather to equivalence classes of such graphs. And we're observing basically here instance of this equivalence relation. So I'll go back to the slides. By the way, are there any questions about this mathematical implementation or simple examples? So going back to the
How quickly it explodes?
It actually doesn't, because that's related to Paul's previous question. It's actually a very simple object under the hood.
What you doing? Combinatorics with matrices in the actual code.
Yeah. So it doesn't need any integrals, even though even for this graph, it was five-dimensional integral. It's not really integral; it's a sum, and it's very quick. I mean, it does explode, but that can be easily battled with more power. Anyway, it's surprisingly better than other things of the same type that we're going to see in a second. And we need to click now something I know. Yeah, thank you so much.
Yeah.
Let's see, that's our definition, that's our theta function. Yeah, so the moves that preserve the answer under which this definition is invariant are called Kirby-Neumann moves. So these are, in the current context, they probably proper name would be Neumann moves, but they're actually instance of something bigger, which is what's called Kirby moves. So here, for inclusivity, they combine both names together. And what this move represents is basically precisely the operation that we saw a moment ago. So we are allowed to make changes to both coefficients, which label our graph, as well as the graph structure, as long as we do it in some correlated manner. And then there are these plus minus ones, which tell us how exactly we're allowed to do this so that answer does not change. So theorem 3, therefore, is a claim that this object, so that's more interesting theorem, that this object.
How many moves you can do on Kirby in order to get Newman?
So is invariant under another name for this move sometimes is 3D Kirby moves, to make contrast with the original 4-dimensional version of Kirby.
So you're thinking of designs of lumping there.
Exactly. So now what we just learned is that this is not a random 4C, it's a plumbing diagram, or whatever this y is, it's representing a 3-manifold. And therefore, what this object that we defined a moment ago is some 3-manifold invariant. So that's used for it in topology. That's where topology comes in. So, but as you can see, nothing so far involved anything fancy. It was something that we could easily explain to undergraduates. So that's why this is fun and easy exercise. So we learned that as a function of q, it's integer q series. As a function of y, it's actually 3-manifold invariant. So then there is another, I'll put it as theorem 4 on the board. Claim. So the question is, if it's a three-manifold invariant, how is it related to anything that we have seen before? And good news, so in some sense, this is where the most interesting, the most non-trivial theorem actually is about this thing. It's not related directly to anything we have seen so far, but if
So what is it counting?
so yeah, that I'll have to tell you a bit later. But as Q goes to root of unity, then it becomes related to something that we can recognize. So it is related indeed, or statement, precise statement is that it gives some of the familiar invariants, which include Witten-Rischiti-Hinterreif invariants. So these are quantum group invariants of three manifolds at roots of unity. So this suggests that whatever this object is, it's a generalization, a generic Q. So it's basically because of roots of unity, it does recover this thing, which also lives at roots of unity. There are many close cousins, for example, Atsuki, Deguchi, Otsuku invariants, CGP, Rochlin. These are invariants of slightly different kind, and some of them maybe I'll briefly show later. But the point is, all of this richness comes at roots of unity, and for generic Q, this is a new object. That's why it's interesting to play with it. I think that's what I say on slides next. Yeah, that's exactly what they reproduce. So this is this collection of statements formalized, and that's a picture illustrating the same thing. As they say, picture is worth 1,000 words. So a generic Q, you have this collection of Q series. Now I don't have to hide from you the fact that this label B has also topological generic meaning. But as Q goes to root of unity, then we actually can recover something that was defined and studied before.
Nice.
But yeah, and of course, if it was only limited to plumbing graphs, so that would be very sad. But I mean, if it's really a three-manifold invariant, you have to be able to assign it to any three-manifold. And famous theorem in three-manifold topology says that every three-manifold can be obtained as a surgery on some node or link. And by now, technology has been developed so that these invariants can be computed. I mean, this Q-series invariants can be computed for many surgeries which are completely outside this class of so-called plumb three-manifolds. So even though what I described to you today in this first part of the talk is for plumbing graphs, this invariance exists for a completely general three-manifold. It doesn't have to come from plumbing. And technology is, again, pretty sophisticated. So computational power, as this slide shows, allows you to compute it from some surgeries of, say, 10 crossing nodes. This is pretty much where computers start to choke for even more traditional invariants like WRT, for example. So in that sense, its complexity, computational complexity is roughly comparable to this WRT. Anyway, this shows that, yes, you can compute it up to, I don't know, some power of Q, the very high power, anything you want. Question is, what are these coefficients? Basically, your question. What are they counting? What are we looking at? So let's go back to this question asked in the beginning. What kind of function of Q do we get starting with initial data of decorated graph like this?
But are there some other moves besides Kirby which gives you the same functions?
Not that I know of. It doesn't have any further redundancies, let's put it this way. Aside from the fact that it's not, of course, unreasonable to think that sometimes different three manifolds give you the same invariant, but so far I haven't seen a single instance. In fact, that's a good question because there are sometimes pairs of manifolds, could be represented by graphs, which give the same WRT invariant, but then this guy distinguishes them. So in that sense, redundancy is here besides what they should be. Nothing is known. And
nothing contradicted that enumerates these classes. Yeah, this invariant.
Yeah, exactly. So that's topologically speaking, that's becomes very strong invariant. So that's a
So
good.
these are actually series, right? They're not, right? So are there issues about convergence or anything, or you're not?
Yeah, so that's where the second theorem comes in. So for all of the manifolds of the class associated to graphs, we can prove, oh, sorry, first theorem, that it converges. Yeah, then it converges. So neither of these examples even is on that class. So these are much more general. And here there are some partial theorems, usually about families. One would say, oh, on such and such family of knots, you compute it. But it's one of the statements which probably is close enough to a theorem because it's like a Sudoku puzzle. If you give me any random example, you can check that it converges, or someone will verify some of the statements here. But proving it in full generality has not been achieved so far. In that sense, it's very much like in computer science, NP type problem. So the answer is easy to verify, but that direction universally is hard to do. So complexity classes, NP.
Is this invariant also related to some non-invariant?
Well, this is a three-manifold invariant because so here what it illustrates, it starts with a knot, and doing some surgery. So for example, here with coefficient +5, it produces a three-manifold. And there are zillions of other knots and links which give exactly the same manifold related to these biturbimes. And one can verify that it doesn't matter with which knot you start. There are different starting points, but by the end of the day, once you implement some of the surgery calculations, you get the same Q series. So in other words, we can verify analog of this statement here for more general surgeries on knots. But again, we're talking about three manifolds. So in some sense, knots are just vehicle or intermediary to get to the manifold. So yeah, then the only remaining thing that I promised you to answer is like, what is the structure here? So what are these coefficients counting, and then so on? Why? I mean, is it a special function or class of functions? And I already gave you the answer, but let me now try to explain why this is interesting answer, or why this is mathematically deep answer. So once upon a time, people played and experimented with algebraic structure, which underlies integrable models, statistical models. And this was around the time that vertex operator algebras were conceived and developed. And people realized, first of all, that many of these share some of the features. So some of these relations these days are called quantum-logistic correspondence, and this works will appear on my next slide. And more importantly, people noticed that important piece of the structure shared by many of these objects, algebraic in nature, could be used to define invariance of knots and three manifolds. That's how the subject of quantum topology was born. So algebra was used as a motor under the hood of a vehicle to produce something topological. So here, since we spent first half discussing quantum group invariance for generic Q, you would imagine that, well, probably, as this statement suggests, these objects are related to quantum groups at generic Q and follow this pattern. So that's true, but that's not the purpose of my talk at all, even though this is true. The purpose of the talk is to say that the result of the calculation, which we saw very explicitly, some specific Q series, kind of, which looks like this, is also an object which has meaning in this world, meaning in the world of algebra. So in other words, we start with a topological problem, we compute some Q series invariant, and then when we thought that already kind of far from algebra and so on, we're just applying it, algebra was just under the hood, it actually spits out an answer which has a deeper meaning in representation theory and in algebra. So that's a surprise. So that's where this Quivers structure will come. So this is a quick slide. So now I'll have to say a few words about some of the developments here back in late 70s and early 80s. So I mentioned the birth of quantum groups, and a generic Q, this is very traditional. So for example, for SL2, which is all I'm doing today, it's defined by usual Chevalier generators and relations. So there is E and F, and K for Thumb type generator. It's completely unambiguous if Q is generic, but if Q goes to root of unity, you immediately get the whole zoo of quantum groups. So that basically is related to what you want to keep or not to keep in the definition, because many things degenerate, and then you need various modifications. The most obvious one is usually called Dickens-Cheney-Cox version of quantum group. Then Lustig version has divided powers. There are also versions defined by Lustig himself, even though they're called differently, such as small quantum group or restricted quantum group and so on, which don't have divided powers. So if you are in quantum or non-commutative algebra, this is a cool thing for you to play with. And life actually starts kind of here on the periphery of this unit disk compared to when we're being here.
So does it correspond to the fact that you have like different invariants?
Yeah, so this plethora of these different options of quantum groups is in fact quite related to the fact that you can get many different things from here. So, and another part of the answer to this question is that what you get here depends on what you do with this additional label B. For example, WRT invariants don't depend on any additional label, so you have to sum over it. And depending on how you sum with what coefficients gives you different.
Did you tell us where B comes from or not yet?
I did very quickly and very tacitly. I didn't want to pay too much attention to it. I said it's a characteristic of a theta function. So if Q is not unimodular, it was a choice that it would have made, and it would be a smart thing to make all choices at once. And, yeah. But from manifold point of view, it's a choice of additional data. So this is actually not just invariant of a three manifold, it's invariant of a three manifold decorated by what our friends in topology would call instance. Right, so this is a very rich story, and I want to do justice of how quantum groups are related to vertex algebras. Usually this is called some version of Cartan-Lustig correspondence. Basically, the point here could be said that for many quantum groups, it's a good idea to ask if a category of its representations is a tensor category and can be realized as category of representation of something else, namely vertex algebra. So this is this yellow arrow, which for generic Q in the form that I needed actually doesn't have an answer here. So there are lots of deep and interesting unanswered questions in representation theory. Here is another example that if we take quantum group and send Q to root of unity and obtain one of the versions of this quantum groups at roots of unity, then its representation category may not be semi-simple, and that's related to so-called logarithmic vertex algebra by this Cartan-Lustig correspondence. And again, there are many variants essentially for many of these things in the zoo here, and this is actually part of motivation of the work that I'm presenting to you to understand which vertex algebras and quantum groups and their tensor categories, how they behave, how they arise. But as I said in the beginning, I try to push this as much as I could to the end of the talk so that we're not talking about categories for the whole hour. So at least 45 minutes we managed to survive without talking about representation categories. But that's the gist of this program. And that's why it's interesting. So what people did in this relation in late 70s and early 80s is they try to understand, that's what Cartan-Lustig correspondence is all about, what these two subjects share in common. And then in modern terms, I already gave you the answer. It's for example, one way to phrase it is to say that they share some parts of representation category. One can also think about the center of the quantum group, which would also have a meaning here, and many, many other objects. But it was kind of surprising, and it again stimulated development of both of the subjects. So the name quantum group didn't exist back in the time when this was noticed. It mainly came from trying to understand some Bethe-Ansatz equations, solvable models of mathematical physics. Vertex algebras were just being developed around the time, so the work of Orchards was happening just around that. And Again, this bridge is very deep and it's still going on, and there is a lot to be done. Like I said, there are some question marks on the previous slide. But one thing people noticed is that you can also try to phrase this relation at the level of something a little bit more pedestrian than categories. In fact, back then they had no notion of categories. This was, again, late 70s, early 80s. That's not how it was phrased. What they noticed is that, and that's what this picture illustrates, that in integrable lattice models and quantum groups, you can talk about a process where some, what would be called quasi-particles, exchange position. So that's what this picture illustrates. And our matrix of a quantum group is basically an operation which tells you what phase you require or what is the cost of this exchange process. Now, this information about our matrix is actually encoded in a quadratic matrix that you find for characters in a vertex algebra. So vertex algebras have representations which are infinite dimensional. So this is, again, field of infinite dimensional algebra. But these are graded, so one can take sum of graded dimensions of representation, and that gives you a character. It's a function of q, which has integer coefficients. So here you should probably start noticing that, yeah, that's exactly similar to what we had before. But here it's, again, this is not modern day. This is 70s and 80s. Or moving to early 90s, in fact, with work of Barry McCoy, who coined the term for this type of expressions. So he said that, or starting roughly with him, this kind of sums are called fermionic sums. Again, this comes from conformal field theory, vertex algebra. It's basically a sum that they had in the very beginning, where you have a quadratic form. So here it's called B. It's a multi-sum over a bunch of integers, non-negative integers, with very standard denominator, and numerator is basically q to the quadratic power. So the point of that work back then was that, first of all, it provided a very cool link to quantum groups. For example, in this cartonistic correspondence, quantum group has R matrix and it has a size. And this B is basically a symmetrized version of the R matrix of the same size. So you could immediately, just by looking at what kind of matrix you have, you could immediately guess what the corresponding quantum group is, and vice versa. So this was extremely useful bridge. So then, of course, there are lots of other things. For instance, this presentation sometimes is not unique. And this is, I think, what Barry McCoy and his collaborators are discussing in this paper and in other papers, such as Rogers Ramanujan identities become meaningful in the subject. And sometimes when you can write the same Q-series in several different ways with different matrices B, it becomes meaningful and so on. So this became very, very rich subject, and by early 90s, it was already taking off the ground very fast and growing very strong. So, but so far, all I want to convey maybe is that this particular sum has a name. It's called fermionic sum in vertex algebra.
What does that Q mean?
This Q, I think it means something else. It means that it wants to, so there are generalized sums of this type, and I think it means some additional conditions. I don't remember. So as you can see, I shamefully just copied it from his paper. And in fact, here I'm showing yet another version, which doesn't have any condition or anything like that. Well, it has conditions here. But as you can see, people sometimes play a little bit with the domain of summation and do kind of variants of this. So this is closer to us. It's using the same term. It calls this fermionic sums fermionic formulae in the context of logarithmic conformal field theories or logarithmic vertex algebra. So this is from Sergei Gukov and Kunin. That's one of the famous papers on the subject, whose very first theorem is basically to prove that characters of some very famous family of logarithmic VOAs are also written in this way. So what I want to convey here is that even if we know nothing about vertex algebra, is that it's not uncommon at all. In fact, it's considered a good idea in that field to write characters as such sums. So therefore, they have a meaning. They call it fermionic.
And so what is the possibility for this matrix A? Is it still some Cartan matrix, or is it like?
Well, it could be any kind of symmetric matrix, basically.
And how?
They're definitely outside of Cartan because just like there are lots of graphs over there, In fact, now you appreciate the significance of first question Ernesto was asking, that the connection, this duality is highly non-trivial. So I don't know, I cannot fully answer mathematically what information about that quadratic matrix is retained by ours.
And are there some Kirby moves?
Yes. So, but that I have to try in a second. Yeah. So very good. Yeah. So for
Can you ask some, just maybe it doesn't make sense. Can you write the elliptic genera of Calabi-Yaos in such form? Because they are kind of like
yes,
traces
yes,
of.
yeah. Because they're characters of chiral
Yes.
algebras. Yes. So like I say, in this business, it's always a good idea. If you have some kind of DOA chiral algebra character, try to think what is presentation in this form. And again, some people made seriously career out of it, like Barry McCoy. So he received many distinguished prizes for his work because he's one of the people who really dedicated his whole life to
He looked at the elliptic genera.
writing. I'm not sure if he did, but probably some of either his collaborators or other people. So, but it's a very good question. So that's exactly what it is. And again, sometimes it's easily found, sometimes not. So it becomes a non-trivial industry and work. But then surprisingly, it comes more recently, this kind of sums, which we call fermionic sums, resurfaced in a different context. So people who studied knot homology associated quivers to knots in some way, which I'm not going to explain. Well, maybe just briefly. So if you have something that's called Humphrey-Petty homology, if it has 3 generators, you would draw a quiver with 3 nodes, 3 vertices, just like what we had before. So the homological t degrees 0, 2, and 3 become the diagonal values of this matrix, or a number of self arrows, and so on. So this became machinery maybe 10 years ago or something like that. And this is enumerative story. So people were interested in either Mativik or other version of Donaldson-Thomas invariants, counting problems of some sorts, which very frequently reduced to a quiver diagram, like this. And then they noticed that basically the answers for various knot partition functions and whatnot can be written in exactly the same structure. So notice the multisum due to something quadratic, universal denominator. So in this field, this type of sums became quiver sums. So the first surprise here is that quiver sum and fermionic form are exactly the same thing. So it's not like people were trying to slide developments of the 80s, not at all. It was completely developed independently using enumerative NDT type algebras, for example, homological whole algebras, representations of these quivers. So they really had different intentions. And they didn't know beforehand that the answer will turn out to be the same. So that was a little bit of a miracle, and this is one of the developments which happened basically just a year or two ago. So until then, these were completely separate subjects, not talking to each other. There would be Cardan-Lustig correspondence and vertex algebras, where this would be called fermionic sums. Then there would be a subject of quiver representation theory, where this would be called quiver sums, but they're really the same thing. And then they bridge different subjects. Better yet, our fellow, my claim, is exactly an object of this type. So I showed you in the beginning, so now let me go back to original part of the starting point of the plot, which was start with some diagram like this, associate a Q series to it. And I showed you that in many cases one can compute it to huge accuracy, but what good is it if we cannot really tell conceptually what sort of object it is? So we can compute coefficients and so on. So first thing one can try to do is to ask how quickly are the coefficients growing. A priori, they could grow with any rate. They could grow polynomially with n here, or exponentially, or exponential of some polynomial of n. Anything could happen, right? Or there could be no regularity at all, and it could be very sporadic. Nevertheless, in every single example that has been computed, what happens is that they grow with a very specific rate. They grow as exponential of square root of n. And this is an important point because this is exactly the rate of growth of coefficients of any vertex algebra, logarithmic or non-logarithmic. So this is something that's a smoking gun. So a DOA person would immediately jump up and down the moment he or she would see this rate of growth. because that's an indication that this is connected to characters of vertex algebras. That's where I said that in quantum topology, usually the flow of information was the other way around. One would use algebraic structure to compute something for topology, and that's it. Topologists will never come back and tell anything interesting to algebraic person. Here, we compute Q-series invariant, and we come back, and it turns out that it has a meaning, surprising meaning, but it didn't have to be the case. That's why I call it a surprise, because it didn't have to be the case that this Q-series has a meaning in vertex algebra, or for that matter, Quivers representation. It could be just a Q-series. It was good enough that it's invariant of a three manifold. That was perfectly fine. But the fact that it happens to be a Q-series of this particular nature with this particular growth is something that is interesting and not fully understood why this happens. So the conjecture is that that's always the case. You start with any graph you want, either Planning graph or manifold in general, and you always find that this is character of some DOA, and a corollary of this statement is that coefficients should grow in a very particular way with a particular. So what we saw is basically a test of this phenomenon. And why this is interesting, because the original motivation for this three manifold invariance was to try to categorify something, meaning to promote numerical invariance to homological invariance. And the fact that, so in fact, that's where integrality of these coefficients would be important. One would want to interpret them as graded dimensions of some vector spaces. And connection to characters of DOAs provides exactly the same kind of interpretation. So one can say that categorification of this Q-series is precisely the module of this vertex algebra, because its graded characters exactly happens to it. So here is an example. So it's illustrating several things. So first of all, it's a concrete three manifold which can be obtained by surgeries on different knots. So one can actually check. This is this NP type statement, but it's maybe hard to prove in complete generality, but one can check in each instance that by doing Kirby moves or computing it in two ways which are related by Kirby moves, one gets the same answer. Then this is actually the expression that we saw on a slide in mathematical computation. We can write it in a more compact form, which is exactly of this type that we wanted, and it happens to be a particular character of logarithmic vertex algebra. So this slide is from, I don't know, 3 or something years old, when this was just noticed, and there were few isolated observations like this, and Mike Friedman was in the audience when he saw the number 42 here. He jumped and said, "Oh my gosh, this is the 42, which is supposed to be the meaning of life from the Hitchhiker's Guide to the Galaxy." So actually here 42 has nothing to do with deep meaning. I mean, it's this particular manifold which actually has numbers 2, 3, and 7 built into it, and that's where 42 comes from. So by now there are many, the structure that I'm describing, this fermionic form or Quivers form, has been identified for many different graphs. So it's growing in complexity, but this is far from the proof. And here allows me 1 more minute. Sure. So I want to finish maybe with a couple of questions. Obviously, this brings lots of questions. Even in the context of these graphs, which was our starting point, one of these questions is to either prove or disprove that coefficients always grow like this. Graph is great. So that's not being done. Another thing is that there is a coefficient here, which is under the square root. Give it a three-dimensional meaning is another question. This also has not been done. So it's easy to do experiments, but we don't know what kind of three-manifold invariant it is. And of course, these two questions will be completely superseded, but probably this will come next, by identifying specifically what DOA characters or modules give us this in general. Yeah, so this is basically a summary of the fact that this object happens to be in Quivers fermionic form. So that's how this fermionic form looks for one of these crazy examples. So there are lots of tests. And maybe one thing I'll mention to just make connection, this will be the last slide, I'll mention to connect it to the previous talk, is even in this world of graphs, recently there was very nice work of Ross Ahmedshad, Peter Johnson, and Slava Grushko, where they considered various generalizations of what I told you today. And for us, it was in the beginning kind of surprise that we start with some integral of some, and it turns out to be invariant under Kirby moves. So these guys studied the entire class of different functions or more different generalizations of this procedure, which is invariant under Kirby moves, and surprisingly found that there are many more. So they may provide a very nice link between what I told you today now and the previous talk, for example. So in particular, they were using some gradient roots and lattice homology of Nemeti to motivate this more general family. So they have this theorem and a definition which says that for some class of functions, then they call it miscible functions, they can produce such invariants under Kirby moves. And again, this is a little surprising because this basically says there are lots of invariants of free manifolds, which ID new, maybe old, but can be constructed in this way, and we haven't really thought about. So this is just to say that this is motivation or indication that this subject is probably closely connected to what people know as Higgs-Floer homology and also the lattice homology of But I'll skip this slide, and I'll just end by showing that what excites me personally is that it's not a single subject. It's very multidisciplinary, as you can see. So if you're a topologist, you may have no interest in enumerative geometry or vertex algebra, but basically you can't escape it here. That's what I find exciting. So sorry for running over.
Thank you very much for the talk. So, is there any question?
Can we both go back to the 42?
This one?
No. So the matrix C is just 1 times 1.
In this case, matrix C is, well, first of all, matrix, yeah, so now I can properly answer some of the early questions. So equivalences on graph were Kirby moves. So analogous equivalences on matrix C were studied in the context of this Quivers. So they're usually called quiver mutations. So these are also some kind of equivalences on moves. This is closely related. I mean, sometimes they're also called cluster transformations, because there is an algebra behind it, and in that algebra they're related to cluster algebra and so on and so forth. So this moves on the quiver side, which was my right to blackboard in the beginning, are cluster transformations or quiver mutations. Therefore, what it says is that this form is not unique. And this is good for people like Barry McCoy because they would have different forms for the same DOA character. So you can ask, so therefore, if it's this or something else, it's equivalence class that we should specify. And the question, what's the minimal size? Usually that's probably more, minimal size of this quadratic form. So here I think that indeed that's basically one-dimensional, so it's very simple. But this, of course, will quickly.
So, yeah, but like, how do you record these numbers 237? Or how do you see them from this form?
That's why I said for Nesta, it's a highly non-trivial map. So in fact, even making a map from graph to Quiver, or this matrix equivalently, is something I cannot describe to you in words. It's a process that goes through this Q series. That's the only way I can phrase it. And if I had a direct way to read off matrix C out of matrix Q, I would say it in the beginning, but I can't.
So
I don't really know.
And do you have it for cipher or like for response spheres?
Yeah, that's basically roughly summarizing the state of the art. Again, this is not the slide I made yesterday, so I probably misses some of the developments, but it's very poor. I mean, as you can see, question marks start appearing here, and interesting things start happening. But basically, what's been done is that for graphs which have only one high valency vertex, this classification has been developed somewhat systematically. And then complexity grows as you increase the number of these legs. So for instance, if you hand me analogous picture with 5 legs. I don't even know what the answer is. Maybe I should, but I apologize. I don't think it's normal.
So on all these series, looks like there is this denominator, the arm symbol. Where is that coming from? Is like is an artifact of the calculation, or because without it, kind of things would not work out, right? So
yeah, and it's so what's under the hood here in enumerated problem is some moduli space. So these Pachheimer symbols often arise as signature in discounting problems when we phrase it as integration of the moduli space as something steady. So the moment we have some GLN stabilizer, we'll have exactly that structure. So in that sense, from Quivers, it's quite natural. So let's see if I have it. Yeah, we're talking about this kind of interaction. Yeah. So yeah, I mean, this universal denominator, it has one meaning in the UA world, and it means something else in the Quiver material world.
can you write a differential equation or something like that, or some kind of for the universal series for the fermionic?
Well, at the base, sometimes some Q-difference equations, but I mean, there is also important distinction between not complements and closed manifolds. Things are usually way nicer for not complements, and there are lots of different structures. Usually, 90% of them break as one tries to cap off the complement and make it into surgery into closed manifold. So therefore, the state of the art is that for me, it's now easy to present zillions of examples where we will see explicitly such fermionic form. In this conjecture where this will hold that its character and it can derive in fermionic form, but it will have no other nice properties inherited from this non-complements. Like so, I don't know. Maybe there are isolated examples, but definitely not really systematic. That we can move that.
So the proof of this identity like goes through some vertex operator algebra parameters, some kind of like Jacobi identity or something like that.
Oh, which proof?
The 237 I started there. Or how do you prove it?
Which statement? That it's a character of
that you get the Macaulay sum.
Right. So in that particular case, and I mean that's what makes it easier. Let's see where it is. I mean, so here it's presented as surgery on 2 different nodes, and already this presentation in its own right can allow you write this object in a closed form, right? So you can write it as a sum. Then the only question is, how do you massage it or prove that it's of this form? So that's much better when you can have some presentation from surgery or topology that allows you to write this down in a closed explicit form.
So you are using some surgery for
Exactly. Yeah, and that's where it's important. I mean, that's why it is so far what has been done. Where is the status? Yeah, here. That's why it's basically going through some surgery presentation, and as you know very well, complexity here is driven by valency of this vertex, so that's the most important layer. That's why explicit theorems, I mean, as a conjecture, it's verifiable for any manifold. That's not a big deal. I mean, one can try to do it example by example, but if one wants to prove it in some families, that's why they start with very small, simple families. Because one has to have usually some kind of closed form expression to start re-expressing it another way. Having something abstract like what we have here is not really helpful because you cannot really prove anything. I mean, you can explore growth of coefficients and other things, but it's more as a check, not as a.
Okay, is there any other question? If Then I have one question. So could you explain the relation between mirror symmetry? As you have one slide.
Well, I had a slide with this one.
Yeah.
It's mirror symmetry in quotes. So it's kind of, it's not the mirror symmetry of Calabi. So it's mirror symmetry because one can ask the following question. So in the beginning, I made the assumption that we actually tacitly used that this graphs were a negative definite. Suppose one wants to switch orientation and go to positive definite. Naively, the definition I gave you cannot be applied, but some of the techniques which we mentioned, like doing 5 different surgeries on different knots, can be applied, so one can compute what this object is for manifold and from manifold with opposite orientation. So in topology, that's a very simple operation. That's orientation reversal. But it induces a very interesting bijection on DOA. So if that conjecture that this Q series invariant is a character of some DOA is true, then it means that this DOA should come in pairs. And that's reminiscent of mirror symmetry for obvious reasons.
Okay. Other question? Comment?
Just the comment, it's beautiful to see how mathematics is getting unified. It's always a big pleasure.
Yeah, that's why I enjoy it. Exactly.
Okay, then
Well,
let's.
thank you.
Yes, thanks. So we will resume at